Okay, so what are we on? Lecture 14. Okay, so today we are going to be doing something a little bit different. So we've covered a lot of material in this class, looking at different types of regressions, doing, continuous response variable to discrete response variables, and then kind of departing from our normal linear models, right, into a lot of these nonlinear, semi-parametric, non-parametric models. And so we're going to kind of do a total pivot right now. And today we're going to be talking about unsupervised learning. So, unsupervised learning is very different from anything that we've done so far because all of the other analysis and approaches that we've looked at are supervised learning, so kind of other category of models. And the specific difference between supervised and unsupervised learning is that in supervised learning, we are always dealing with a response variable, a y. Okay. Here, unsupervised learning is just about examining undetected patterns in data. And this focuses on settings with only explanatory variables. So no response variable. So not interested in prediction. This is about identifying subgroups among variables. And you are unable to conduct validation. Okay, so whereas with our regular regression models, we're trying to understand relationships between variables. With unsupervised learning models, we are only concerned about understanding patterns in the data. Okay, so no response variable, so obviously no ability to do validation, right? With validation, we have these relationships between variables, and then you can check what that looks like with data that's out of sample. Here, you're just looking at patterns in the data, and you have nothing necessarily to really validate against. So, one of the big areas in unsupervised learning, which is mainly we're going to be focusing on today, is clustering. And so I'm going to walk us through today a number of different clustering approaches. Maybe some of you guys have heard of some of these methods. Maybe some of you guys have used them before. And we're going to try and understand a little bit about how they work. And then that will allow us to have a better understanding of when they should be used and how they actually operate. And we're going to apply them to a couple of different data sets so that you guys can see, visually, a little bit more explicitly, how different clustering can operate. And I think that's really important, right? If you're ever doing any of these like clustering operations, a lot of times people just pick and choose clustering methods that they're familiar with. but they should be applied in certain ways, and hopefully we'll see that. Okay, any questions? Okay. So, clustering approaches. So the first one we're going to look at is known as k-means clustering. This is maybe the most common one. Who's done k-means before? Anyone? A couple? One, two? Okay. This is also known as centroid clustering. So this is a simple approach to partition data into k distinct non-overlapping clusters. And importantly, k must be pre-specified. Okay, as always, I'm going to start with the math part first, and then we'll talk about how this actually works. So for your reference, it looks something like this. Minimize C1 through CK, k equals 1, up to big K of 1 over absolute value of CK, sum I prime, elements of CK, and then sum from J equals 1 to P of xij minus xi prime j squared. And this is the number of observations in kth cluster. Okay, what the heck does this mean? Let's walk through an algorithm, kind of like we've done in the past, on how the clustering assignment actually happens, and then maybe the math becomes a little bit more understandable. So, algorithm. First, we randomly assign one minus k to each observation. And then we iterate until no more changes. For each k cluster, compute the centroid. Then B, assign each observation to cluster with closest centroid. This is using the Euclidean distance. Okay. Because we're using Euclidean distances, this is maybe similar to something we've talked about before. What do we need to do? So suppose I wanted to cluster let's see. Uh, suppose I wanted to cluster, like, I don't know, fuel efficiency and the number of pistons in your engine. So if we're looking at observations on these two scales, what's the range of number of pistons in an engine? Like 2 to like 12. And what's the range of fuel efficiencies? It's like 10 to like 50, right, in a car. So if we're doing based on distances, the clustering is going to be focused on, it will divide things more on fuel efficiency than number of pistons, right? Because the distances will be larger just by virtue of the size of the units. So what do we need to do here? This is just like our K and N. Any ideas? Scaling, yeah. You basically want to make it so that the range of values are the same. So here, note scaling, normalization is critical. Okay? Okay. So yeah, I'm not sure why the nomenclature is like they say assign 1 minus k, but maybe just to clarify. Suppose we have a bunch of data here, something like this, and something like this. Step 1, when it says do this random assignment, essentially what we are doing is this. I'm just going to pick some random points in the data. So we'll go here, and I'm going to assign it into a particular group. We'll do something like this. And then we're going to do something like this. Okay. So that's it. That's step 1 of the algorithm. I'm just randomly assigning my data into my categories. Oh, I should be explicit, right? I am doing k equals 2 here. I have a red group and a blue group, and these are going to be my 2 k's. Okay? So that's step 1. What do I do in step 2? Who can help me out here? It's literally right there. Any volunteers? Yes.
Does that mean you switch where the blue dots are with the red dot?
So the iteration means I'm going to do 2A and 2B again and again until nothing changes. Yeah. But what is 2A? Compute the centroid. Okay, so where is the centroid of the blue dots? I'm going to say it's like slightly more to the right than to the left because we have more blue points there. So let's just say the centroid is about here. Okay? Where is the red centroid? The red centroid is, well, they're divided 4 and 4. I'm going to say it's like halfway in between, right? So the centroid is maybe over here. Okay? Seem reasonable to everybody so far? Okay, now for each observation to the cluster, assign each observation to the cluster with the closest centroid. So let's do that. We'll just go through this one by one. So, this point, oh, I'm not going to do it in a dotted line. This point, is that closer to the red or the blue centroid? Red, yay. Okay, you get red. How about this guy? Red, and this one, this one, this one. Okay, so we're going to color that in red, and that one's also closest to red, right? Okay, so hopefully you guys can see where this is going. We will color this in. Great. And we'll do the same thing for all the points on the other side, and hopefully you guys can all see, right? They're all close to the blue one. Yay. Great. Now let me get rid of these centroids. Okay, and now we will iterate. Back to step A. For each K cluster, compute the centroid. Okay, now where's the red centroid? It's probably like somewhere here. And where's the blue centroid? It's like here. Okay, step 2B, reassign observations to the cluster that each point is closest to based on the centroid distance. Okay. Anything changing? Okay, great. So, no changes. So we're done with step 2, and that's it. Those are our 2 clusters. Okay. This one happened to complete in one step. That won't always complete in one step, right? But the idea here is that you're essentially like looking at points that are kind of closest to you, and that is how you determine the cluster size. Okay? Okay, any questions about this?
What exactly
Yes.
do the points mean, like if you were to assign a data set?
So it could be anything, really. You are trying to understand, like, how essentially close data within your data set are to each other. Okay, so what would be some, like, practical examples of this? Because the data I'm going to show you is actually not that practical. It's just more to understand the differences in the clustering. Actually, we could look at some of our old data sets. So the wages data set, for example, we have, what were they? So your wages, your like education, gender, that sort of thing. So without making a determination about how they relate with one another, you could see if like high income people tended to also kind of correlate with like more education, years of education, right? And so you might see these clusters where you see a distinct one, like, oh, people who had 4 years of education tend to have this cluster of salaries, and another one had a different cluster. So it's a way in which, if you don't know anything about the data, you can start to understand some of the like patterns in data. It's very common to do clustering, especially on like spatial data. And so if you wanted to understand how things are like spatially clustered in certain ways, you could use these types of algorithms to help you with that. Okay? All right. So let's jump over to R. There are 4 data sets that I have uploaded to Canvas that we'll need for this, for the examples that we're going to do today. So go ahead and download those if you have not had a chance to do that already. And we're going to use a couple packages. I'm going to start with these 2 for now. And we'll do loading in the data. So example 1, we'll do this thing. Example 2. Example 3, banana, and example 4. Oop. Okay, and we're gonna just start off by plotting them, just so we can see what the data looks like. Two, three, 4. 2, 3, 4. Okay, please don't be. Please work today. Oh, obviously gotta load all this stuff. Yes, okay, great. Okay. We have 4 different data sets. And you can see how the points are arranged across my X and Y axes. On the top left, it's an arrangement of 4 blobs. Top right, it's an arrangement of a lot more blobs. Bottom left, we have these 2 horseshoes, and then bottom right, it's basically shapes that are determined by higher density of data in certain regions. Okay? So we're going to cluster our data and see what happens when we use k-mean squared across different sets of examples. Okay, so we're going to do k-means example. So we are feeding in the data that we would like it to look at. And let me actually pull this up just to make sure. Yeah, okay. There's actually 3 columns here. We're ignoring the last column, which is why I'm doing this. But this is this bit here. The first entry into the k-means function is just your x and y columns in which you are trying to do clustering on. Although you can cluster in more than 2 dimensions, right? It's all just Euclidean distances. So you're not limited to just doing 2 axes, but you wouldn't be able to visualize it. Okay, so if we run this, let's see what happens. What's the output of this? So I run k-means on 2 with 2 clusters, and this is the output after it runs that algorithm that I was just describing, right? What we just did manually. It tells you there's 657 points in one cluster and 604 points in a different cluster. It tells us what the means of the clusters are for your x and y. So cluster 1 has a average value of 37 in x and 12 in y, and cluster 2 has an average value of 85 and 52 in y. And then here in the clustering vector, it'll actually tell us for every single point that you have, which cluster it assigned it to. So for data points 1 through 650 something, it assigned cluster 1, and then after that, all the data points are assigned into cluster 2. Okay. We have some tools here, and I'll talk about some of these a little bit later. But let's actually take a look at what this looks like. So I'm just setting up the ggplot. Okay, so this is our first example that we were just showing before. And you can see that when we ask it to just have 2 clusters, it has done so and separated out the data into 2 groups. And if you can imagine, based on all our algorithm that we just described in the example that we walked through manually, you can probably imagine how it had done this assignment and arrived at this particular configuration. Okay? So we don't have to right, so one of the things is that with k-means clustering, right, as I was mentioning, you have to specify the number of clusters at the beginning. This isn't like a determined thing. And so what would it look like if we were to change the number of clusters? Okay, so this part, don't worry about following along. We are just repeating this example that I just put down, but for a different number of k, and then operationalizing that into something we can visualize. So I'll walk through this in a second. Yeah. So I'm running, I'm going to run a custom function called varyk, where I am essentially looping through from 2 clusters up to some number of clusters that I specify, and then grabbing the results from that. So here we go. We'll do that. We'll run it up to 10. And let's look at the ggplot. Okay, so if the top left is the one we just looked at, right? So splitting 2 clusters, so we have red and brown kind of divided up. Okay, and what happens if we were to do 3 clusters? We would have our mud green right in the left. On the bottom we have the brown, and then in the top right we have the red. So that's with 3 clusters. Okay, so with 4 clusters, you might imagine, oh, you know, there's these 4 distinct groups. Each one is going to be its own cluster. But actually, if you look at cluster 4, you see what ends up happening is actually, instead of switching out the two red clusters into their own cluster, the left cluster gets divided in half. And the bottom one stays the same. Okay? Why do you guys think that happens? Why might that happen? What do you guys think? So if we think about the way the algorithm is operating, one thing that could be happening is that you could have like a really high density of points in an area that will affect that will pull the centroid distances a lot more than trying to separate certain groups. And so this is one of the features that a k-means cluster might run into, is issues with like point density. So that's something to be careful for, watch out for with k-means. So you can see what that behavior looks like as we proceed through adding kind of more and more clusters. You can see in some cases different clusters get split up, and that it can also have to do simply with the assignment of points in the starting iteration. So that's one thing to note as well. So it may not always operate quite in the way that you think. Okay, and so you can see as we do different Ks, as we go through all of these iterations, what the clustering outputs look like. Any questions? Okay, so what is the correct what's the correct way to determine K? Any ideas? Incorrect. So, yeah, trick question today, because we can't do validation on on any of this. And so actually, there isn't really a right answer. This is like subjective because you get to decide how many clusters there are. People have thought about some standardized techniques to employ for determining the number of clusters. I'll talk about kind of the most common one. It is called the elbow method. So if you, okay, where is it here? So one of the metrics that, oh, not in here, in here. One of the metrics that came out of the output is the total within sum of squares. This one. That is, that's the ratio between the total sum of squares and the within sum of squares. You can think of the sum of squares as kind of like the error distance from a point to your centroid. So it looks at within each cluster, the like distances from every point to that one, and then it compares that as a ratio against the distance to the total sum of squares across all the data points. And people have used this within sum of squares metric as a sort of kludgy way of determining how many Ks that they use. Oh, hang on. So, if you plot your within the sum of squares against the number of clusters, you always get this sort of exponential curve that looks like this. And the elbow method is like, if you pretend that this is like an arm, it's like where your elbow would be. So that might be like 3, 4, 5, I don't know. It's rough sometimes. And so that's usually where you're essentially saying most of the like distance variation has been captured by the number of clusters. And as you add more clusters, you're not like reducing the like distances to the centroids that much, right? So that's what this is saying. And so one of the common ways that people determine a K is this elbow method. Okay, any questions about that? Yeah, so that is the application of k-means to our first example. And what I would like to do now is show you guys what this looks like for our other examples. So give me a second here. Again, no need to follow along. We're just repeating basically the code that we did identically for our other examples. Okay. Yeah, this, for example, would be the elbow method for our second example. And so your elbow, I don't know, might be somewhere in this area. So maybe around 10 clusters would be optimal. But let's take a look. So example 2, and I'm going to pop this one out. So we have a lot more. We have a lot more data here, and you can see across all of this data how I'm dividing out the clusters. So if we think of each of these little groups as ideally a cluster, right? Clearly we have too few clusters kind of at the beginning. The elbow method is telling us maybe around cluster 10, 11, that's when we should stop. Although in this particular case, I might argue that there's more clusters that maybe, I don't know, like 17 or 18 might look pretty good to me, where each of those groups actually is getting divided and assigned into a new cluster. Okay? So trust your judgments, double check visually if possible. You can see what this looks like here. Any questions about this? Okay, the next example was the like 2 horseshoe, right? I guess we would consider there to be a pretty distinct cluster of points there. And so let's see if it is doing what everyone expects. So let's do example 3. Okay, so if we think of each ring as an individual cluster, right? So we would have 2 clusters, but if we look at our implementation of k-means clustering, you can see, well, when the groups are kind of overlapping in space like this, the centroids are assigning parts of my horseshoes to the other group. And if you think about it, right, it makes sense. The centroid is going to be closer to some of the points in the other group because it overlaps in space. So the assignment ends up happening like this. Okay, then you can see kind of can't really get rid of that as we move to more and more clusters. Okay. So for this type of thing where you have spatial overlap, k-means clustering. Yeah, if we were to say that those were 2 actually separate distinct groups, this might not be the best technique to do that. Okay, and the last one. This is the kind of crazy one. And this one has a lot of points, so it's kind of harder to see. Actually, let me plot just that one on its own so we can see in just a little bit more detail. So it looks like this. Okay. And the images are based more on the density of points. So you have like this equal sign, we have our 2 horseshoes, we have this little hook thing, and then a circle with 2 dots in it, or an oval with 2 dots. Okay, so for that one, when we run this guy, you can see that none of those patterns emerge. And so shapes that are based off of density are not going to be well defined by clustering based off of centroid distances. Okay? Okay. Moving on, unless there's any other questions. The next type of clustering we're going to look at is known as hierarchical clustering. This is also known as agglomerative or bottom-up clustering. This is an alternative method. And the nice thing is, does not require pre-selecting K. And this will result in a tree-based representation known as a dendrogram. Okay, so, oops. I'm going to draw a tree right now. And for the moment, don't worry too much about how these points or how these lines are determined. We will talk about that. This one goes down to here. This one will go down to here. Okay. So if I have something like A, B, C, D, these are known as our leaves, and these guys, these are known as branches. Farther up the tree, branches will fuse. The more difference the leaf, the more different the leaf observations are. So the farther up you go, the more different they are. Not based off of distance horizontally, okay? It's always distance vertically. So I don't know if A is closer to C and D than it is to B. That's going to be determined by the vertical distance. The way that the tree is set up allows us to determine an arbitrary amount of clusters. Okay, and so it kind of maps out all the clusters for you in the tree automatically, and then you can determine what groupings are assigned based off of the tree. So for example, if I wanted to look at two clusters based on this diagram, then I would do something like this. I would do a cut here for two clusters. Okay? Right, and so I've cut those two branches, and so I have a group of points here, which is one cluster, and then I have a group of points here, which is my other cluster. And what if I wanted to do three clusters? Well, then I could do something like this. I could do here. So I cut here for three clusters. And you can always do this for any discrete amount of clusters that you want. Cut here for four clusters. Right, and so if I had four clusters, then my clusters would be one cluster of points here, one cluster here, one cluster here, and one cluster here. Make sense? Great. No questions? Okay, so let's talk about how this works. Algorithm. So each observation is its own cluster. So we have n total. Then the two most similar are fused. So you have n minus 1 clusters. And then we continue until only one cluster is left. Okay? So pretty simple. I look at all my points. I look at the two that are the closest. And then I fuse those two. And then I look at all the points again and then continue fusing up and up until I have the full tree. So I said on the basis of distance. So similarity on basis of Euclidean distance. And that works just fine for individual points. How do you fuse a cluster? How do you fuse a point into an existing cluster? Right? So now let's say you have 2 points that are already fused, and then there's another point that you're trying to determine whether that belongs into this group. Do I look at this point, or okay, wait, let me just draw it. Right, so suppose I have 2 points, and then I have a third point that I'm trying to figure out. Do I look at the distance to the closest point? Do I look to the distance to the farthest point? Or do I look at the distance to like the centroid of those points? Right. And the answer is they're all options, okay? So you can do this. So similarity on the basis of linkage. And our linkages are called complete, single, and average. So this is largest dissimilarity. This is smallest dissimilarity. And this is average dissimilarity. And that corresponds directly to these three examples that I just drew out. And what I will note is that average and complete tend to have more balanced clusters. And by balanced, I mean an equal number of points in each cluster. And we're going to see this, a pretty extreme example of this, right, when we apply this to the four examples. Okay. Any questions about this? I think the concept is fairly straightforward. I think the more important thing is building up the experience to understand what these clusters are doing. And so that's what I'm trying to do with the code. I think I'm not going to have you guys really follow along here. I'm going to walk through the code instead, just so that we have enough time. So don't worry about trying to type all of this stuff up. Let me get rid of some of these things here. Okay, so, okay, one more, sorry. We've got our four examples again. And here, we are applying hierarchical clustering using a function called hclust, which stands for hierarchical clustering. We use a function to calculate the Euclidean distances called dist. And then the method that's getting applied at the end of this function, complete, average, and single, is just in reference to the type of linkage that I was talking about, right? So where complete is looking at the point that's farthest away in a group versus the average location of the points in the group versus the closest point in the group. So we're going to look at all three of these. And the first thing I want to do is show you guys what the actual tree looks like. And there, I think you'll be able to see the differences in what that means to the structure of the tree based off of these three. I mean, it may seem like a small thing, just making a decision about how I group a point into a cluster, but you'll see it actually makes a really big difference. Okay. So here, this is obviously a much bigger tree. You can see, though, that if I snip across the branches to make two clusters, I've got a set of clusters kind of on the right, and then, or set of points within that cluster on the right, and then a whole bunch of points on the left, and they're like roughly-ish the same size. And I can kind of continue doing these cuts, and you see that the groups are like relatively balanced, right? Even as I go down farther and farther, you can kind of see by the like equal size of the branches distributed across a length that actually those clusters are going to be similar in size. What does this look like for average? Kind of similar, but the clusters may be, slightly different and slightly different sizes, and they may form a little bit differently. But so generally speaking, I should say complete and average are going to look pretty similar to one another. Whereas the single one is going to look very different, very unbalanced, right? So now look what happens if I snip across and divide into two clusters. There's only a small bit on the left-hand side, and then there's a whole bunch of points on the right-hand side. And so using the single method is going to be a lot less balanced. And we'll take a look at the application of these across those 4 different examples to see what that ends up doing for us. So there's kind of like more dimensions to look at here. Yeah, so I wrote some code to help me do all of this at once. And so let's look at the application to our first example. Okay, so I ran our first example through using the H-class algorithm. I built out the trees for all 3 types of linkages, and then I did cuts to show us what the groupings look like for 2 through 10 number of clusters. Okay. And you'll notice as we look through, let's look kind of vertically at cluster by, at the same number of clusters across different linkages types. So both average and complete, if you have 2, they've separated them out into the like left and bottom versus top and right ones. Whereas with single, you can see it's just one cluster at the left that's red and everything else is a different cluster. So already with just 2 clusters, it looks pretty different. And then you can see with 3, they end up looking similar. 4, yeah, so if you look at 5 and 6, this is where some of the weirder clustering behavior shows up. So in single, you have the red cluster, the bottom cluster, and then our 2 clusters, and then there's a single point out there that is its own cluster in single, but that ends up getting grouped into other, with other points in the other ones. Okay? So, the linkage makes a really big difference in the way the clusters are determined in hierarchical clustering, and that's one thing that you definitely want to kind of pay attention to. Any questions about clustering so far? Okay, so let's take a look at the second example. So this will be just for complete linkages. Actually, let me go back real quick. I should say one more or ask you guys one more thing. How do you guys feel about this hierarchical clustering versus k-means for this particular example? Based on what you've seen, which one would you rather pick? This, what was that? Yeah, and that's because, if, right, I agree, and I think that's because visually we're seeing these like 4 clusters, right? And we saw that the k-means algorithm was unable to differentiate them spatially in the appropriate way. Whereas here, we actually see all 3 linkage methods will divide these clusters maybe into the ones that we expect, right? So with example 2, maybe that's a little bit harder to say. At least for me, I'm looking at each of these groups, right? And seeing if, as I build out my clusters, am I actually ever able to differentiate, each of these groups properly? Yeah, and it's kind of hard to say. A lot of times, this particular linkage will be splitting certain groups in half, as opposed to trying to divide other groups out of a larger cluster that's like spatially disconnected. But so I think both the k-means and the hierarchical clustering are going to be similar in these types of applications. And I think the linkage choice here may help a little bit, or will definitely make a difference, particularly if we look at the first 2, the average and complete that I'm showing now, versus the single, which should look, I think, fairly different. Yeah, it is more in the single clustering linkage under hierarchical clustering. It's more about finding the points that are like the most different from your cluster, as opposed to trying to group things that are the same. And so you'll tend to find in single clustering larger clusters that would have been divided by my average and complete clustering, but that some of the like spatially separated points will get assigned their own groups first. Okay? Okay, what about the horseshoe? What do you guys think? How are we gonna do? You think we're gonna be able to separate the horseshoes properly? Let's take a look. So, the average and complete are going to work kind of similar to the k-means, right? But the single, right, it is about looking at things that are the most different from my group, And here, it like very clearly defines these as being sort of very close to each other. And in fact, it has like if you look at thinking about the distance from these sets of points to any other set of point in here, it has a really hard time trying to pull these things out. And in fact, as I go from 3 to 4 to 5 to 6 clusters, it's like kicking out like individual points out of my cluster, right? It's hard. It's not going to try and make sort of individual groups, and so that's where the single linkage can really shine, is when you really care about the like closeness spatially. It will try and keep things together as much as possible. Okay? All right. And then number 4, the crazy one. Do we have any chance here? Nope. Still trash. Okay. Any questions about hierarchical clustering? Yeah.
You were mentioning if it was better than the K clusters, but isn't one of them more about the density of data points rather than the actual shape that they are in the product? As a way of clustering.
You're talking about in the last example or just in
I
general?
think we were looking at example 1 for both
Yeah.
hierarchical and K clusters, and when you asked which one would be better.
Yep. So I guess okay. So let me reset for a real quick second. So if I were to I'm being maybe a little bit facetious here in the sense that like there isn't, with unsupervised learning, we're not necessarily there's like saying a right answer, but if I were to ask you to like group this into some number of clusters, your intuition would be what, 4 clusters, and it would be the 4 clusters, right? Yeah. And so if that's kind of our sort of validating factor, even though, right, we're not like formally validating anything here. If I were to do, oh, wrong one. It's this one. This is k-means, right? So here's k equals 4. It didn't divide these two into 4 clusters. It did 1 cluster, 2 cluster, 3 cluster, 4 cluster. That's k-mean. And then in hierarchical,
It was each little box.
yeah, in fact, all of them ended up getting separated. And that is, yeah, one of the features of, yeah, with k-means, like it does to maybe some degree a little bit of density, and that might be what it's throwing off, but it mainly cares about distance. Yeah. maybe one of the things that, actually, let me plot this again, the original one. So I think one of the things that might throw us off is that it's mainly about distance. And so there's a question of if the distances between the centroid here and there are bigger and smaller versus the centroids across these points here. And I think what's happening is that the scale is not super accurate, because if I look at this distance, it's like almost twice as wide as this distance. So if I were to make it more accurate, maybe like this. Yeah. So that's visually, you have to make sure it's kind of lining up. Okay. Any other questions? If not, let us jump to our final example of the day, which is a clustering method known as DB scan. This is density-based spatial clustering of applications with noise. I prefer DB scan to the long title. Okay, so given a set of points in some space, it groups together points that are closely packed together. So points with many nearby neighbors. Marking as outliers points that lie alone in low density regions. And dbScan has two parameters, which we will talk about: the minimum points and epsilon. So let's walk through how this works via an algorithm, as we have with our last two examples. Okay, so for each point in the data set, if number of points within epsilon neighborhood is larger or equal to the min points, classify as a core point, otherwise label as noise. And then we will, step 2, expand cluster. For each point, that is a core point, form a cluster. Any core points that can be reached is part of the cluster. Any noise points that can be reached but is less than or equal to min points, add as border of cluster. Okay. What the heck does all that mean? Let's do a little example. All right, so I have to draw this a little carefully here. Okay. We have 2 parameters that we're going to set. So we're going to have our min points, let's say, equals 4. And then our epsilon is going to be a distance about yay long. Yeah, that looks okay. So epsilon. Okay. So what I'm going to do is for every single point, I'm going to draw a circle around it with a radius epsilon. So we're going to do something like so. And this is okay. I'm really bad at drawing circles. Okay, we'll just go like that. Okay, so there's my first circle. And you're going to do this for basically every other point. So how many points are within this circle? 5. Is that more than or equal to our min points? It's more than, right? So then this would be labeled as a core point. Okay, oh, let me do this in black. We're going to call this a core point. So we're going to repeat this for every other point in here, and you will find that these are going to be labeled as core points, and this is going to be a noise point. Okay? So that is step 1 of our algorithm. So all of the core points that are reachable to each other from the epsilon is going to be a cluster. And this one here, if I were to draw epsilon here, maybe this circle will reach the noise point actually reaches to the core point, but it's less than the number of, it doesn't reach our min points requirement. And so this would be known as a border point. And same with this one. This would also be a border point. But they would be technically considered part of that cluster. Okay? This point here, so epsilon doesn't reach any other points. So this would just be noise. Okay? And that is, essentially the procedure for dbScan to do its clustering. So a very different procedure, right, from what we've did with k-means and what we did with hierarchical clustering. This really cares about how close points are to one another. And that's mainly set by the parameters of these min points and our epsilon. Okay, so let's look at dbScan. One sec, let me get rid of some things here. Okay, so for dbScan, we do need a couple of other libraries. Again, this is just to follow along, and then we'll provide the code so you guys have this for reference. We have dbscan package, fnn package, and fpc. Okay, so first question is, how do I determine what the right min points should be? And oops, here we go. We can do a similar procedure with the elbow plot for dbscan, where we change the minimum number of points. And the idea is you should go with essentially, you should go with the one that reduces the point sampling elbow the most. And so in this case, the elbow point isn't actually changing much across these plots. And so, here we're deciding on, 3 points on the basis of that. Although you can also, in some of these examples, we might look kind of visually, right? But if I were to do that, and I set a, sorry, for epsilon, I'll also show what it looks like to vary that as well. The epsilon point can be chosen based off of this elbowed plot as well. So that's where the actual kink is happening on the y-axis. This is the distance metric. So here it's about 0.8, and we can see using density with a minimum points of 3, we end up with these different clusters. Okay. I should note, actually, these are different clusters, and all of the colored points on the edges are the border points, and all of the black points that you don't see that are uncolored, those are the noise points. So density matters more than distance. Okay. We can look at what happens as we vary our epsilon. One moment. Right, so epsilon is that radius search space. You're essentially saying, oh, the smaller my epsilon, the closer I require my points to be. So if you remember in the original plot, the spacing between the points is not always the same. And so when epsilon is really small, that cluster, the least dense cluster, doesn't end up clustering a lot of points. You have some, you may have multiple clusters in there with some border points, but most of it is going to end up as noise. And as we expand the epsilon, we're saying, oh, we're actually okay with there being points that are slightly farther apart, that are less dense. And so more and more of that low density cluster gets included into one cluster, right? And you can see that the density of the other 3 clusters is like relatively similar. And so straight away, those ones all get grouped together, although you do have some more border points and more noise points out of those 3 clusters up until, you know, maybe 0.9, and then those all stay kind of the same. But the biggest difference is with that cluster that is the lowest density, you can see how increasing the epsilon, increasing that radius, absorbs more and more of those points into a single cluster until we're at epsilon 1.5, and most of the points have been included. Okay. We'll do the same thing here. Don't worry about those. Okay, so here is our second example. Oh no, not again. Sorry. Right. Yeah. It's on line 200. Okay. All right, let's try that again. Here's example 2. As we increase our epsilon, right, it's encompassing more of the clusters. But when you have many of these groups that are like at different distances from each other, the way they get absorbed into clusters is going to be maybe a little bit wackier than maybe some of the other algorithms. And so here, the density may not be a great way of differentiating. What do you guys think for example 3? So, oh, actually, so example 3, which is our horseshoe example, see what happens. Yeah, and so the points themselves, the density is low enough, small epsilon, you're not able to get clusters, but once you're at the point where you're kind of encompassing the distance points, the general distance between points in these ones, it is able to differentiate our clusters pretty well, right? Because the space between points in an individual horseshoe is like a lot smaller than the distance jump to the next horseshoe. And so dbScan does work for this example. Okay, and example 4, this is our last hope for the one that none of the other ones could do. I don't think I got there yet. Is it plotting? All right, 1 second. Ah, okay. I think it's running right now. This one may take a little bit longer. Right. So here, where the images are sort of entirely produced by the density, you can see if our radius is too large, it will sort of blob out again. But at a sort of the right epsilon size, if you have the right search space, we're actually able to differentiate the patterns pretty well, right? I don't think we ever quite get the two circles inside of the oval, but like at epsilon 7, for example, we get the two parallel lines, we get the horseshoe, we get the hook and the circle in the hook, we get the oval, and then we get one of the circles in the oval, but not both of them. Right, and so here we can actually differentiate patterns and clusters based off of density, and that's one of the things that dbScan is really good at, or was designed to be good at, where some of our other clustering methods will fail. Okay. All right, any questions? So this is our kind of foray into unsupervised learning. We don't spend a lot of time here, but clustering in itself, it can and is a, can be and is a pretty, good tool for data analysis, particularly when you are not looking or trying to understand the data. If you're not looking for relationships explicitly and trying to understand the data, this can be a good way to suss out patterns to potentially do data analysis on and switch to kind of supervised learning. So that's it for this. For your projects, I'm gonna try and get feedback to you either by the end of the week or early next week. So expect that to be coming shortly. That's it. Yes.
And it was okay that only one person per group?
Yes, I'll only need one person as long as all of your names are on it. Yeah. Okay, I will see you guys next week.